So we'll have a look at this velocity versus time graph here, just as kind of a reminder of some things. Okay, if we want to find the acceleration from a velocity versus time graph, we're essentially finding the slope of a line that exists between those 2 points. Even if a line doesn't actually exist between those 2 points, that's essentially what we're doing, okay? Because the formula for acceleration is final velocity minus initial velocity over time, which from this graph would be like y2 minus y1 over x2 minus x1, right? The time, it'd be the change in velocity divided by the change in time, right? That's where that formula comes from. So even if there isn't a line between the 2 places you're being asked about, you can still calculate the acceleration, okay? All right, so it says here between A and B. Fortunately for us, there is actually a line between A and B, okay? So we can figure that one out. What's our initial velocity? 0. What's our final velocity? 20. How long does that take? 2 seconds. All right, so that's a pretty easy one, right? So we're going to go 20 minus 0 over 2 seconds, okay? And we're going to get positive 10 meters per second squared. Why do I have to put the positive on there? Right, it could be either one. Acceleration is a vector quantity, okay? Just like velocity and displacement are vector quantities, acceleration is a vector quantity. There's no scalar version of acceleration. Acceleration is always a vector quantity, so it's got to be positive, negative, right, left, north, south. It's got to have something on it, okay? All right. Second part of that question asks us to calculate the displacement between A and E. All right, now, if I want to calculate displacement, that means I've got to take average velocity and multiply it by what? By time, okay? Really, we're just manipulating this. Okay, we're manipulating it to solve for what we're looking for. Now, the tricky part here is the average velocity. Places where the velocity doesn't change, average velocity is easy. It's just whatever the line is at. Okay, so for this section here between B and C, the average velocity during that time is, is 20, because it's a velocity time graph. Right? On a position time graph, you're right, it would be 0. Okay, but this is a velocity time graph. So the average velocity during that part is 20. Okay, but here in this first part, it changes from 0 to 20. So what's the average velocity during that part? 10. Yeah. Okay, because half the time it's going slower than 10, and half the time it's going faster than 10, and it's uniform. Okay, if it was a curve, that wouldn't be true, but this is uniform, right? That's why we can go and find the area of this triangle and have it represent the displacement, because really, this is what we're doing. The average velocity, okay, is basically the height of this triangle divided by 2. Is that how we find the area of a triangle? Base times height divided by 2, right? So that's really what we're doing here. We're just still following this formula. All right, then we have a triangle that looks like this, okay? And we have a really tall rectangle that looks like that, and we have a rectangle under it. Okay, everyone follow me there? This is the part that people tend to forget on a graph like this, is that this area in here still counts. Okay, this still counts as displacement that the car has undergone, or the object, whatever it is, has undergone. Right? Because in this section here where C is, it's already moving at 20 meters per second, and then it speeds up. This area here represents how far it would have gone if it had stayed at 20 meters per second. Then we add on to that how far it goes after it accelerates even more. Does everyone follow me there? So all of that area still counts. We've always got to find the area between the line and the x-axis when we're trying to solve for total displacement. Okay, so now it's just a matter of some area calculation. So we got 20 times 2, which is 40, divided by 2 is 20. Okay, this rectangle here is 20 times 2, which is 40. All right, this rectangle here is going to be 20 by 1, 2, 3, 4, so that's going to be 80. Okay, this triangle here, how tall is it? 20, right. It goes from 20 to 40, right? Don't make the mistake of assuming it goes all the way down to the bottom, because it doesn't. Okay, so its height is 20 and its base is 1. So 20 times 1 is 20, divided by 2 is 10. Okay, and then the height of this rectangle here is 20 and its base is 3, I think, right? 1, 2, 3. Yeah. So this is 60. All right. Now we've got all of our shapes calculated. Now, do you have to draw exactly the same shapes as me? No. I mean, if you wanted to draw one big rectangle in here and calculate that, it doesn't matter. As long as you're calculating the whole area, you're going to get the same numbers I do. All right. So we got 60, 120, 130, 220. Oh, I must have missed something. I got 210 on there. Did I add wrong? Yeah, I did. I added 90 and not 80. It's 210. Still early, I haven't had my coffee yet. Okay, so 210 meters, okay, is our total displacement. What's wrong with the answer I wrote there? It's a vector quantity. What needs to go beside it? Positive. Yeah, okay. And honestly, guys, I know it seems nitpicky, but that would be wrong, okay, on a test. If you don't have that positive there, then it's not a vector quantity, it's a scalar quantity. Okay, we don't just assume that because it doesn't have a sign that it's positive. All right, is this making sense? Ringing a bell? Okay. Part C asks for the acceleration between F and G. All right, so what's the acceleration rate here? 0. Yeah. Okay. I hope a lot of you are looking at me like you were thinking that, but you didn't want to say it. Okay. The velocity at F is 20. The velocity at G is 20. Did the velocity change? No. And acceleration is the change in velocity over time. If there's no change in velocity, there's no acceleration. All right. So you can kind of automatic. That's one of those automatic things where it's like, oh, it's flat. Well, then it's not changing. Right. That's one of those things that applies to any graph. If it's a flat line, it's parallel to the x-axis, then there's no change. Okay. Now, I've put a question like that on a unit and a final exam and made it out of 1 mark, because that's all it's worth. You just look at it and know that it's 0. And you would not believe the work people do for that question. Okay? Always look at the point value of a question. If it's out of 1, there's no work. Okay? It's simply an answer. It's always a dead giveaway. I've had people go on to the back side of the page doing all this work to prove an incorrect answer. Okay? Like they didn't want it to be 0, so they did all this work to prove that it was something other than 0 and wasted a lot of time. Okay? So always look at point values on questions. They give you a pretty good idea as to what kind of stuff you need to do for that question. If you've been working on it for 10 minutes and it's only 1 mark, leave it. Okay? It's only 1 mark. Don't keep playing with it. Okay? All right. Average velocity between A and F. What 2 things do I need for average velocity? Total displacement and total time. Well, I've already got the displacement to E, so I only need to do like that triangle and that rectangle, and I'll add that onto that, and then I'll have the displacement all the way to F. Agreed? Okay, so this one's 20 times 2, okay, so that one's 40, and this one will be 20 times 2 over 2, okay, so that'll be 20. Okay, so we got to add 60 onto 210, so our total displacement's 270 to that point. And how long did that take? 10 seconds. Okay, so we get positive 27 meters per second. Okay, is any of this like really mathematically difficult? Not really, right? I mean, we're doing some multiplying and dividing, a little bit of area calculating, which is like what, grade 5 geometry, right? It's nothing serious. Okay. All right, and then F, the total distance traveled. All right, so do I have to find the last few shapes here? Yeah, and then I add them all up, and I don't make them positive or negative. Okay, I just add them all up for that one. All right, so if we're looking at that, we would have 20 times 1 over 2, okay, which would be 10. Okay, and then we'll have, this is 10 high by 1 wide, so this is 5, and this is 20 high by 1 wide, so it's also 10. Okay, All right, so we have to add on to our 270, 295, right? Oh, what did I miss there? It's 20 for the last rectangle. Yep. These should both be 20. I got to drink my coffee. That's all there is to it. Okay, so we'll get 315 because I was 20 short. Yeah. Okay, everybody with me there? Okay, let's finish that up, and we'll go through any ones that give you trouble here. Okay, and then we'll move on to acceleration. Acceleration will be easy, basically just talking about that formula. Okay, so it won't take us very long to go into that. Okay, so for a normal object, okay, that is an object that has no forces acting on it, okay, or at least no unbalanced forces acting on it, what is it going to do? What is an object that basically doesn't have anything going on going to do? Nothing. Exactly. Okay, this table right now that's sitting in front of me, gravity is pulling on it, pulling it into the floor. The floor is pushing back with an equal and opposite force, okay, and as a result, the table sits there. Okay, the table is not going to jump into the air, nor is it going to hopefully fall through the floor. Okay, it's not going to slide to the side, at least not on its own. All right, so the natural tendency of objects is to basically sit still, unless there's an unbalanced force acting on them. Okay, that's actually what Newton's first law is. Okay, Newton's first law can be summed up in one word: inertia. Okay, the inertia of an object is the tendency of an object to continue doing what it's already doing in the absence of other forces. All right, so most of the time that means that things don't move. Okay, things sit still. Okay, but it could also mean that if an object was moving at a constant velocity, that it would continue to do so. Okay, now on Earth that's difficult because there's always an unbalanced force on Earth, and that's friction. Okay, friction is always slowing things down. It's always working against you. Okay, so rarely do we see something on Earth just continue moving at a constant speed. Okay, now if you put your car on cruise control, okay, on the highway, then you can travel at a constant speed, because your car continually applies force from the engine to offset any hills or things like that, right? And so it typically has a balanced force situation and then travels at a constant speed. That's what cruise control is for, to keep you at a constant speed. In space, however, you can see this, okay? If something gets moving in space, there isn't anything to slow it down or speed it up, unless it gets close to a planet and gravity starts to pull it. Okay, but if it's just out in kind of interstellar space, it's going to move at a constant velocity. That's why space probes like the New Horizons probe that went by Pluto earlier this year, okay, they don't have to carry a lot of fuel on board. Basically, they need the launch vehicle to get them moving really, really fast. Once they separate from the launch vehicle, they've got that speed. Okay? They don't really need to do much else, right? They'll use the gravity of other planets to kind of slingshot them a little bit once in a while, but for the most part, they just travel on because there's nothing to resist their movement. Now, they do have engines and they do have fuel, but most of that is not to make them go faster. It's more to change their direction if they need to make a course correction so that they don't crash into something. Okay, that's mostly what they use their engines for. Okay, New Horizons is actually the fastest object ever made by human beings. Okay, moving incredibly fast. Okay, it made the journey from the Earth to the Moon in like hours, right? Instead of the days that it took the Apollo missions to do it. Right? So it was an incredibly fast spacecraft. It's also incredibly small, right? So it didn't have a lot of mass to move around. But once you get moving, your tendency is to keep moving at a constant velocity. Now, if I want to speed up, then I have to apply energy, okay, and I've got to apply a force, okay? That's what we're going to be dealing with. We're going to be dealing with the situations where there is a force being applied, it's not balanced, and it's making the velocity of an object change. Please. Oh, it's not a burning fuel kind of engine, it's more of like a pressurized gas kind of an engine. And when we do, in ones where there is combustion, the combustion occurs and creates pressure within a chamber, and then the chamber can open and that pressurized gas shoots out, right? So the hot gases get they exert more pressure than cold gases, so they shoot out, and that creates a thrust. Okay, they push on the inside of the spacecraft, okay, and the spacecraft pushes back, and that's the force that shoots them out is, okay, the spacecraft pushing on them, they push back on the spacecraft, and the spacecraft moves forward. Yeah, it's Newton's third law. That's how all rockets kind of work. Exactly. Yes, just like in WALL-E where he has the fire extinguisher. Okay, that's Newton's third law in action. Okay, and in fact, if you notice that he kind of gets the hang of it like throughout it while he's pushing it or moving it in different directions, right? Like if he pushes it up this way at an angle, he moves the opposite direction. Okay, now do the gases coming out of the fire extinguisher move a lot faster than WALL-E? They do, because they have way less mass than WALL-E. WALL-E's bigger, right? So the gases move a lot, and the spacecraft or WALL-E moves a little. Okay, so inertia, basically the tendency of an object to remain at rest, or an object in motion to stay in motion unless acted upon by an external unbalanced force. Okay, when it is acted upon by a force, then its velocity changes, it accelerates. Okay, so that's Newton's first law is that. Okay, it's not, well, it's part of rocket science, but in and of itself, it's not rocket science, because if you like look at a situation where Newton's first law applies, it's like, yeah, duh. Okay, Newton's first law says that that chair is going to sit there. Well, of course it's going to sit there. There's nothing pushing it. Okay, but that's how science works. If you're the first person to put it on paper, it's yours. Okay, no matter how stupid and simple it is. Okay. All right. Okay, so for acceleration, okay, acceleration is occurring whenever the velocity of an object is changing. Now, in Science 10, that's going to be one-dimensional. Okay, it's going to be getting faster or slower. Right? When you get to Physics 20 and we start bringing other directions into this, a change in velocity can mean just a change in direction. Okay, you don't actually slow down; you just turn. All right, that's also an acceleration, because in order to turn, do you have to apply a force? You do. Okay, when you turn a corner in a car, what keeps you from sliding? Your wheels, the friction between your tires and the road. Friction is providing a force that's turning you in that direction. You're still accelerating, okay? And you know that because if you're in the car, you want to keep moving in a straight line, right? Especially if the person driving is crazy and they take the corner really fast. Okay? Then you have this, you're thrown into the door. Well, you're not actually thrown into the door, it's just that you want to go in a straight line and the car is turning. Okay? So you move to the door because your inertia says, I want to move at a constant velocity. And that means I have to move in a straight line. Right? Same thing that happens when you get an icy corner, right? You're coming into that corner and you're going too fast, you hit the brakes, you try to slow down, and then you try and turn. What do? You keep going straight, okay? There's not enough friction to make you turn. You keep going straight into whatever is over there, okay, that you were trying to avoid. All right. Okay, so the meaning of average acceleration is best shown. There should be a space in there. That's a terrible typo. Okay, can be illustrated by considering a plane during takeoff. Okay, so average acceleration, or we might even say uniform, might even be a better word. Uniform acceleration is best shown by a plane taking off. Why is a car accelerating away from a stoplight not a good example of uniform acceleration? What does your car have that planes don't? No, they have a steering wheel. It's called a yoke, though. Gears. Okay, when you accelerate away from a stoplight in a car, your gears change as you accelerate. And if you've ever driven a car and kind of noticed this, first gear pulls a lot harder than fourth gear. Okay, you don't accelerate at the same rate in the higher gears as you do in the lower gears. So your graph of acceleration for a car ends up looking like this, and it kind of flattens out, okay, near the top because you don't accelerate as much at the end. Whereas for a plane, without gears, it's pretty straight. Okay, it's nice and uniform. So we use a plane as a better example. All right, so what happens while the plane is taking off is that its velocity changes over the course of time. Okay, so during an elapsed time interval. All right, and that's where we get this formula from. Okay, we said this formula here is really just the slope of that line, okay, on a velocity versus time graph. Okay, so if a multiple choice question was to ask you which of the following is a good description of acceleration, okay, you would be looking for something that mentions what two things? What two things are changing? Time and velocity, right? Okay, so you'd be looking for an answer that had something about changing velocity and changing time. All right. So, simple example here of how to calculate acceleration. We'll use this plane here as the example. Okay, when it's at rest, okay, and that's a key word. Okay, starts from rest. Okay, if it starts from rest, how fast is it going? 0. It's resting. It's not doing anything. So, questions will try to trick you by making it seem like they're not giving you very many numbers by making the numbers words. Okay, and rest is one of those words. If it starts from rest, it starts at 0. If it comes to rest, it ends at 0. Just little things like that, little wording things we got to watch for. Okay, so the plane accelerates down the runway, and 29 seconds later is traveling at 260 kilometers per hour. Okay, so the plus sign indicates that the velocity is forward, positive. Okay, all right. Do I want to keep my velocity in kilometers per hour, or should I turn it into meters per second? Yeah, I should probably turn it into meters per second. Have we gone over how to do that yet? I think I might have done it once. Okay, but we'll review it here. Okay, if I want to change kilometers per hour into meters per second, I've got to change 2 units. I've got to change my units for distance, and I've got to change my units for time. Okay, so that means I have to multiply by conversion factors. All right, so in 1 kilometer, there are how many meters? 1,000. Okay, so if I multiply kilometers per hour by 1,000, I'll have meters per hour. Agreed? Okay, so I'm partway there. Now I need to convert my hours into seconds. How many seconds are there in an hour? 3,600. Okay, so I've got to take whatever I have in kilometers per hour, multiply it by 1,000, and then divide by 3,600. So really, what I'm doing is this: kilometers per hour times 1,000 over 3,600. Okay, that's what I'm multiplying by. Is everyone okay with that? Here's the easier way to remember this. If I'm multiplying by 1,000 and then dividing by 3,600, is that the same as doing this? Right? Is that the same as just dividing by 3.6? Right? If I multiply by 1,000 and then I divide by 3,600, what did I bother doing that for? If I'm going to divide by this big number anyway, why don't I just divide them both by 1,000 and be done with it? Right? If I divide both these numbers by 1,000, I get that kilometers per hour is really converting to that. Right? It's just a conversion factor. It's a ratio. Right? 1,000 over 3,600 is the same as 1 over 3.6. Agreed? In terms of a ratio, right? If you divide them both. Well, if I multiply by 1, does it change my number at all? Okay, so can I just go kilometers per hour divided by 3.6? Okay, that's how you do it. You want to convert kilometers per hour to meters per second? You divide by 3.6. Okay, that's how you do all compound conversions. You don't have to do very many in Science 10, but when you get to Physics 20, Physics 30, there's more compound conversions. So you've got to know your metric system a little bit, okay, when you get to that. Okay, so let's go back to this example here. Okay, now they've left it in kilometers per hour and they're going to divide by seconds, but then they're going to get weird units. They're going to get kilometers per hour per second, which, I mean, they're still valid units, but they sound weird. Okay, sounds kind of weird. So let's divide this number by 3.6 to get meters per second. Okay, so we'll take our 260 and divide by 3.6. All right, so we got 72 meters per second. Okay, minus 0 meters per second, right? The initial velocity, and then divide that by the time, 29 seconds. So really, this is what I've done. Okay, VF minus VI over T. Right? So now I'm going to have 72 over 29. Actually, I should just use the answer there. All right, so the acceleration is 2.49 meters per second squared. What do I need on this? Positive. All right. Would you feel that if you were in the plane? How would you feel with that acceleration? Yeah, it'd be G-force. You'd feel pushed into your seat a little bit. Okay, anyone ever flown on a plane before? Okay, right? That's how you feel, right? When you're accelerating down the runway, it's like, whoa, and you're leaning back in the seat, and okay, and it's pushing on you. Okay, because you're feeling an acceleration. Okay, and that acceleration, what you feel is really the seat pushing on you because you're trying to sit still, and the seat's pushing on you because the seat's attached to the plane. Okay, everyone follow me there? Same as how a seatbelt works in a crash. Okay, if you get into a crash, you keep moving forward because you're not part of the car. The car stopped. Okay, you keep moving forward. If you have your seatbelt on, you're part of the car. Okay, because then you're attached to the car. Right, and then you will hit the seatbelt, and the seatbelt will stop you. If you're not wearing your seatbelt, then Newton's first law will have you leave the vehicle, not through the door. Yeah, that's why seatbelts are important. Newton's first law can get you killed if you are not using your safety devices properly. Yep. Yeah, absolutely. And if you've ever gone over like kind of the crest of a steep hill, it feels like all your guts are kind of moving up a little bit, right? Okay, same thing, right? You're going over the hill, you're moving at this angle, right? Your organs are moving at that angle, but you're attached to the car. Suddenly the car starts to move back down, and your organs are still going up a little bit, and you're like, oh God, heart's in my throat, kind of thing, right? Okay, that's all caused by Newton's first law. Okay. Okay, now we talked about this already, how we get the meters per second squared, so we're not going to dwell on that too much. Okay, are we going to be asked to solve for things other than acceleration using this formula? Probably. By probably, I mean definitely. Okay, so are we going to have to be able to manipulate this formula? Yes. Is it a little tougher than v equals d over t? Yes. Is it a little tougher than y equals mx plus b? No. Okay, in fact, it's no different than manipulating y equals mx plus b because that is y equals mx plus b for a velocity versus time graph. Okay, it's just manipulated for m right now. All right, let's say I want to solve for t. What am I going to do? Multiply it. Right, I can't solve for it if it's on the bottom. Okay, so I'm going to move it over here, and then what? Divide by a, right? So it comes over here. Everyone all right with that? Okay. Now my t is going to separate into small parts. Okay. I want to solve for VF. What should I move first? T. Yeah, I got to move T first because it's not attached to VF, is it? Right? VI is attached to VF, but T is not. It's below it. So I can move T first. Okay? T is going to come over here. Now what do? I'm going to add VI to both sides. You wondered why I had that up there, didn't you? It's my plus sign. Okay, so now I've got VI plus T times A equals VF. Everybody okay with that one? All right. What if I want to solve for VI? Well, actually, I can't just, let's say from here, if I want to get VI by itself now, what should I move? The T and the A, okay? So think about this, guys. This is like order of operations. You guys remember order of operations? Right? You do parentheses and then exponents, then multiplication, division, right? Would I have to multiply these two numbers, T and A, together before I added it to VI anyway? So is T times A really just one number? Okay, so can I just subtract it over to the other side? Yep. Okay, so that's what I would do. Go away. Oh, go all together. There we go. All right, so VF minus t times a will give me vi. And that should make sense, right? This is the bigger of the two, likely, if I've got a positive acceleration. Okay, vf minus the change in velocity should give me what I started with, right? Okay, whereas the other way, I was taking what I started with and adding how much I changed by in order to get my final velocity. Okay, making sense to everybody? All right, it's going to take a little while, a little bit of practice, but you guys are getting pretty good at your algebra here, so I don't think you're going to struggle too much with that. Oh, now it wants them all to be 1 again. Okay, so I screwed it up. No, I want it back to this. There we go. Okay, everyone okay with how that manipulates out? Okay, let's try a couple of examples here. Okay, I want you to write this one down. Okay, and then we'll do it together. This is the easiest one, obviously, because it's asking for acceleration, and the formula is already set up for that. So this one shouldn't be too difficult. First thing, write down your givens. Starts from rest. So VI is 0 meters per second. Okay, reaches a velocity of positive 16 meters per second, so that'll be our final. Okay, and it does that in a time of 4.5 seconds. Okay, so A equals VF minus VI over T. Now, here's the importance, guys, of writing down your givens. Okay, I was asked to find acceleration, and I was given these 3 things. Is there any other formula on your formula sheet that you got yesterday that has those 4 things in it? No. That's why you want to write down your givens. If you're ever lost and like you read a question like, I have no idea which formula I'm going to use for this, write down your givens and then match them up. There's only going to be one formula on your formula sheet that'll have all the things you have and what you're looking for. Okay? Now, once in a while, you might have to combine 2 formulas, but you'll know when those situations are. On the test, I'd probably give you another one. Like I usually just put this on the front page, just because I don't know how much you'll write on yours, right? Okay, so now all I have to do is plug in my numbers. So VF is going to be 16 minus 0 over 4.5. So 16 divided by 4.5. All right, 3.56. Actually, let's say 3.6 meters per second squared. Now, caution. When you're punching this into your calculator, if this isn't 0, you do need to put the top in brackets. Okay? Because if you don't, your calculator will do what? It'll divide first. It just does order of operations. Okay? So it'll go 0 divided by 4.5 and then go 16 minus that. And so you'll get the acceleration to be 16, which it's not. Okay? So you got to make sure that you kind of circumvent what your calculator is going to do. Okay? Make sure that you enclose that in brackets first. All right? So what do we get there? 3.6, right? Meters per second squared, positive. Okay? Indicating it's speeding up. Okay. Everyone all right with that one? Okay? So same as always, I'm going to show you one for each manipulation of the formula. Danielle. Usually 2 decimal places. Yeah. Yeah, for the final answer. Yeah. Okay. How long will it take a jet to accelerate? So how long? What are they asking us to find? Time. All right, so time is our question mark here. Okay, will it take a jet to accelerate from rest? Okay, to 85 meters per second at a rate of 22 meters per second squared. Okay. So we have A this time, VF and VI, and we're looking for T. Okay, how do I get T by itself? Right now I'm dividing by T, so if I want to move it, I have to do the opposite, so I multiply, and what I do to one side, I do to the other, okay? And now I want t by itself, so I divide by. All right, so I'm going to have VF minus VI over A equals T. All right, so that's going to be 85 minus 0 over 22. Okay, so 3.86. 3.86 what? Seconds. Okay. Daniel? That's up to you. If it helps you keep track, go ahead. If you don't need it, don't worry about it. Just make sure your final answer has one. Okay, anybody still need that one? Okay, number 3 is asking us to solve for what? VF. All right, so VF is our question mark here. Okay, the race car, if it starts at 15 meters per second, so VI is not 0 for a change, okay, and accelerates at 7.2 meters per second squared for 6.5 seconds. Okay, now I always put the, what happened to my 1 there? I always put the signs or the vectors in my givens. All right, and that's just me, but I always want to have it in there so that I remember this one's positive, this one's negative, especially if the question gives me east and west or right and left. I want to put in my givens right away, positive, negative. Then I'll go back at the end of the question and go back to whatever the vectors were that I was given. Okay, but I want it to be kind of mathematically correct in my givens. All right, so we've got A equals VF minus VI over T. I'm solving for VF. Rules of algebra say move what's not attached first. T is not attached to VF. Okay, so I'm going to multiply both sides by T to bring it over here. And then what am I going to do with VI? Add it. All right, so now I've got my formula to solve for VF. So when we do that, VF is going to equal positive 15, okay, plus 7.2, positive 7.2 times 6.5. All right, so everything's positive in that question, okay, so that works out easy for us. 15 plus 7.2 times 6.5. This time I can let my calculator do order of operations because that's what it's supposed to do. Okay. All right, so I get that the final velocity of that, whatever it is, okay, is going to be 61.8 meters per second. Positive 61.8 meters per second. Okay, everyone all right with that one? Okay, so the last manipulation is the trickiest one. And I'm going to go over both ways to do it because there's actually two. Okay, I have a preference for myself, but okay, I'll show you both ways. Okay, so number 4 is asking us how fast was a boat traveling initially if it accelerated to 30 meters per second at a rate of 2.6 meters per second squared for 8.9 seconds. So what am I looking for here? VI. Okay, the acceleration is positive 2.6 meters per second squared. VF is 30 meters per second, and the time is 8.9 seconds, and that should be positive as well. Okay. Give you a chance to catch up with me there. Okay, so our formula starts out like this. A equals VF minus VI over T. Okay, I need to get VI by itself. So there's two ways to do that. The first step is multiply by T no matter what. Okay, you got to multiply both sides by T, Now, some people like to take VF and subtract it over to this side. Okay? But if you do that, VI isn't positive, is it? It's negative. Personally, I don't like to solve for negative numbers because I know that for myself anyway, I'll forget that I solved for a negative number and leave the vector the way it is instead of switching it. Okay? Because if I solve for negative VI and it comes out negative, it's actually positive. Okay? And I know myself, I'll forget that. Okay? So I always solve for something positive. Okay, so you could just subtract VF over to this side and you'd have T times A minus VF equals negative VI. You could do that. Okay, I'm not really comfortable with that. Okay, I don't like doing that. So what I do instead is I add VI to both sides so that now it's positive, and then I bring T times A over here. Okay, okay, by subtracting T times A over to this side. So I end up with VI equals VF minus T times A, which is the opposite of T times A minus VF, right? Okay. So now I can plug in my numbers. Okay, that's going to be positive 30 minus 8.9 times 2.6. I don't know why I put brackets around that. I don't need brackets, but I did. Okay, so basically this is figuring out how much I'm going to change my velocity by, the 8.9 times 2.6, and then I subtract that from what my final velocity was, and I'll get what I started with, which is 6.86 meters per second, positive. Okay, that's all the manipulations you're going to have to do of that formula. Okay, when you get to physics 20, I give you 4 more acceleration formulas on top of that one. Okay, but for science 10, that's the only one that we're going to deal with. Okay. Questions on how that works? Everyone's good with that? Okay. How many people have done the graphing thing completely? Okay. Let's finish up the graphing thing. If you're already done, you got a couple of minutes here where you can do something else. Hey, tomorrow I'll give you the worksheet on acceleration after our quiz, which will be posted later on today, and it will be on graphing. There'll be 2 graphs.